Hello, I'm Robert Chodorek. I'm from AGH University of Science and Technology, Poland. I would like to present a paper entitled Improving the Efficiency of WebRTC Layered Simulcast using Software-Defined Networking. Last years showed that it's very important. It's human activities in the internet, especially web transmission, video conferencing, audio conferencing, e-learning. Many of these activities are use web services. To use these web services, we need some tools. WebRTC technology, web real-time communication, gives native real-time communication on the top of the web browser. It's not necessary an additional plugin to this web browser. WebRTC technology is currently embedded in most of popular web browsers and integrally connected, integrally built in the web browser. This technology gives users application program interface. This is in this part, and including inside we have a full stack for video processing, both from capturing images from user camera and encoding this data, and on the end user and allows to decode this video and present and selected by the user devices. Also we have not only coding, but also we have some additional element to provide better transmission of this video and some additional mechanisms to provide better quality of experience of this video. For audio we have also codec, and we can capture input devices on the user system and present on the speaker or headphones in the end user our audio. Also we have additional mechanism to improve quality of experience of this system. Including in these technologies, it's transporting services. It's a secure version of RTP protocol. Secure version of RTP protocol allows to transmit real-time data like audio, video. And also we have some multiplexing services which allows to send several streams, audio, video streams, several tracks inside, for example, audio to end user. Technology, it's also this part of this stack. It allows to peer-to-peer connection behind network address translator, behind firewalls. It required some additional protocols. It's a framework ICE which allows to goes through these elements. When we go inside, protocol stack used for the transmission base is a UDP transport protocol. It's a special typical conferencing system. WebRTC technology generally allows to establish peer-to-peer connection. It's required additional elements, for example, signaling server, which allows to exchange data between peers. ICE protocol for one end to get full data about connection, one part. Another system get from ICE protocol information about connection in another part of network. And signaling system exchange data between this two web browser According to this data, this web browser can establish connection directly between and system. Also required sending some information about transmitting stream. It's encoding using SDP protocol. When we have multiple user, multiple connection to deliver multimedia content to the end session participant, it's some challenges. Its users are located in different places, not only one place. When we have point-to-point connection, it's quite simple because one user is one part of the network, next in another part. In this, when we have multiple users, we have this user located in different places, which different characteristics of links, different timing characteristics, different throughputs, and we require to send to the user high quality stream to the satisfactory quality, and user use a different conferencing tool. Generally, it's a different application, different version of this application, different type of hardware with different resolution, and etc. To deliver multimedia content to the end user, we use typical centralized system. It's built in a star topology. It's a typical solution for many, not only WebRTC system solution. And the central system, central point of the star, it's a conference bridge. Typically, this conference bridge might be simple or more advanced. For example, can build a virtual reality from source from multiple participant in this system, and when get data from multiple system, can resend this data with record quality, and can change this conference bridge stream from another form to different, can change resolution, can change frame rate, can change generally quality of this stream. And in most complicated version, it's a problem with performance of this conference bridge, because each decoding and coding of multimedia stream required a high computer capacity. Therefore, this conference bridge is typically strictly limited to the session of the, for example, 25 participant, 100 participant. It's depending on the cost. Another type of solution for this conference bridging is using selective forwarding unit. In this solution, conference bridge not change quality, not change this transmitted stream, not decoding and encoding in different format, but only selectively forward the desired stream to the end user. For example, only send video from active user to rest of the user, only selecting this video. But it's some problem with this sending system, because when we selectively forward this information, we can only forward one stream, only one stream with desired quality. To build more flexible system, it's proposed Simulcast to this WebRTC technology. The Simulcast technology was proposed in a draft version of almost 4 years ago, but work about the Simulcast is still, because the latest version of this draft is dated about 2 weeks ago, and Simulcast allows to encode the same content to different streams. Each stream can be encoded in different quality. It's a one solution, or in different layers. One base layer, it's base quality, typically low rate, not required more network resources, and additional layer add some information to the stream, and this information improve quality of received stream, for example, more details, improve resolution, more frames, it's more smoother video transmitted. And when we use Simulcast, this stream it's encoded in several streams or layers and go to the selective forwarding unit. And we have a system like this. It's one sender sending 3 different streams. These streams are it's transmitted within one session. It's in our example, it's a layers, base layer and additional layers. Layering system can we propose to move some functionality from selecting forwarding unit to the switches, SDN switches. Each SDN switch can act as a traditional selective forwarding unit. In this solution, SDN it's not only a working element which acts as SFU, but also put some information about network condition. We merge this information from receiver and information from SDN network, condition about this SDN network, and we put the controller. And our system, proposed system, it's like this. From SFU, we send some information to the SDN controller, information about active session, about performance and selected stream. We also get information from the switches, information about, for example, available bandwidth in each part of the network, for example, in this link, how it's copied, and about link to the end user. And based on this information, the SDN controller sends information to the switches, which layer will be allowed to receive in each system. Therefore, SDN switches can send to the end user on the layer which this user required, and also layer which meet capacity of links between source and between sender and the desired receiver. We test our solution in a large multi-gigabit European academic network, and this network offers some testing capabilities. We can set testbed as a service. It's one capabilities of the service. In our test, we used 8 nodes located in different European cities, and we sent information from running web browsers in these cities to the end user located in different cities. We use some emulating capability of web browser. Web browser can get data directly from the camera, local camera, or we can use redirecting this input source as from the file, and we recording some sequences, pre-recording the sequences, and next we transmit from several nodes in this testbed network. And this is our topology and connection between nodes. We send this data between these cities. We have 3 versions of experiments. The first it's experiment with recognize static limitation of each links and each path from the sender to the receiver. And this system must be fit to this current state of this network. Next to it's a dynamic capabilities when competing video stream with the bandwidth, or when this video stream compatible with bandwidth not only each other but also with TCP flow. TCP flow can consume the rest of available bandwidth. It's it's a good background traffic. First, we analyze typical system. 3 layers it's used. First part it's connecting to layer only 1. Next 2 layers it's transmitted that for finalized stream received by receiver. It's like this. It's about 1400, 1002 kilobits per second, and when it's connected the last third layer, it's about 2 megabits per second. But link it's strictly limited to 2 megabits per second. Some of this stream it's larger than 2 megabits. Therefore, we observe large errors in this system. The system cannot easily recognize physical limitation of the network. When we put in our proposed system, it's in the first part is similar, next part is similar, but the third it's not connecting to layer 3 because it's a physical limitation. We have get information from SDN network that this link is limited. Therefore, it's not decision to connect to the higher layer. We not probe to enhance quality of transmitted stream. Therefore, we have no errors in this system because it's a good recognition of built-in topology. When we transmit multiple streams, when it's one simulcast stream, one layer, it's several sessions, no errors because these links can allow transmit this with no errors. When we have 2 layers, it's some problem when we have multiple streams because it's a limitation of link. In original system, it's when we have multiple streams, it's a higher error, and in our proposed system, this error is very small because we get information about network condition from SDN network. When we have multiple TCP streams, errors are smaller because TCP traffic, background traffic, we observe in the link, get some faster information in congestion control in RTP protocol based on information from RTP protocol, and this layer it's not connecting to higher layers. In our proposed system also errors it's very low. To conclude, the experiment carried out in testbed network, a large testbed network, showed that network node loaded packet error rate it's very low. This method of congestion control it's better, and SDN controller included in the process of selecting layers can react quickly and autonomously. Using both information, we receive better quality, and quality of experience is quite good. Thank you for your attention.